Hello, can you hear me? We can start the session. So today we discuss the self-supervised learning. So in self-supervised learnings, we aim to learn the representations of the data um, such that they are useful in the downstream tasks. And this downstream task can be anything such as segmentations, classification, etc. So uh, um, some of the popular self-supervised learning techniques are methods are based on the rotation. Here, given the data x, we compute the rotation of the data and say the rotations are 0 and 15, 60, 120, etc. So we associate the label corresponding to x with respect to the rotation of x with this thing say the call does label 0, 1, 2, 3, and 4, etc. Now we treat this rotation index as the supervised task. Now we are sort of training the model to predict the rotation angles. And once we train these model using the regular cross entropy loss, or where the labels are the rotation angles and the on the data. Now, once we train the model F, we can take this model F and use these representations f of x, and finally train a simple classifier and tune only the classifier on the downstream dataset. So this works pretty well, and this is one of such technique. And another technique is uh, maximizing the agreement between the positive and negative examples. So given the data X, we create a positive pair, positive augmentation and a negative augmentation of this data. And we just try to maximize this contrastive loss where we want to maximize the agreement of the representations of the data point with its positive augmentation, and minimize the agreement between the negative examples. So this kind of loss is called as contrastive loss. This is one way. This is another way of learning the representations using the unlabeled data in a self-supervised way. And finally, we'll go over one of the popular techniques called as SimCLR. Um, Given endpoints, end data points, x1 to so on, xn. Since CLR creates augmentations, and the augmentations are crop, random crop, and color, and Gaussian blur. Gaussian blur. We can pick any of these augmentations and apply to the set of endpoints to create the augmented versions. Excellent. So now we take this data point and we create the augmentations. X1 and X1 tilde, and then we pass it through a network F and get the representations. And this is then passed through a non-linear function G. And here the agreement is done. So the loss function that is being used here is um, exponential of Zi and Zj transpose divided by sum of exp of Zi times K transpose I not equal to K, and we take we want to maximize this agreement between Zi and Zj, and Zi and Zj are the correlated augmentations. So we want to minimize this non-negative log of this. So given two augmentations of the image, say x1, x1 tilde, x2, x2 tilde, and so on, xn, xn tilde. x1, x1 tilde, x2, x2 tilde, and so on, xn, xn tilde. Now we pick one row, and here for this one row we want to maximize the agreement between x1 and x1 tilde, as it is a correlated augmentation of the image of the one image, same image. But we would like to minimize the agreement between x1 and x2 and so on, xn, between x1 and xn, etc. Similarly, for x1 tilde, we would like to maximize the agreement between x1 tilde and x1, and this term we ignore it and don't care this term. Similarly, we would like to minimize the agreement between x1 and x1, x2, x2 tilde, and so on. This thing. So for each row, we try to compute the loss. For example, the first row we would like to maximize the agreement between f of x1, f of x1 tilde, transpose delta x of this thing, and then divided by exp of f of x1 transpose of xj tau sigma j not equal to I plus xp of h1. Here in this xj, all this the tildes also will count. Um, so there will be 2n minus 1 terms here. Similarly, for x1, maximizing the argument between x1 and x1 tilde, and here between x1 tilde and x, we maximize the argument, and x1 tilde and x1, and we average these two losses, the loss of x1 and x1 tilde plus loss of x1 tilde and x divided by 2, and finally this is computed for n points, and then finally this is averaged. So once the training is done, the nonlinear part is removed, and we only use the f part of the encoders, and then this f is used for the further downstream tasks. So this method is called as SimCLR. We now go over the notebook. Um, so in before notebook, we also have to discuss something called as clip. Um, Contrastive language image retraining. In this, this is a vision language model. So this models uses vision transformers for vision models, and transformers for the text. The way these models are being trained is given an image xi. Um, this is passed through a vision transformer. It's called as image encoder. Call this as image encoder or resonance transformer. Here we generate image representation, and for the same image, we present a caption, such as if the image has a cat, so the caption would be a photo of cat. Text encoder. So we get Z text. So we pass say n images Zi1, we get n representations Zin. Similarly, we get n text descriptions Zt1, Zt2, and so on, Ztn. So here we would like to maximize the agreement between the images and its corresponding text. So on the diagonal, we pick here, and so Zi1 exp of Zi1 transpose Zt1 divided by sum of exp of Zi1 transpose Ztj. J goes from 1 to n. So this clause ensures that this image embedding is pushed close to T1 and pushed away from the remaining text descriptors. The same thing can be done from the perspective of text as well. So here we take the other way around. The text is being matched to image representation of first image and being pushed away from the image representations of the other images. So this is the loss function of the clip, and the way to do the zero shot prediction on the clip is so once this pre-trained clip is loaded, and let's say we have to perform a classification from 10 of 10 CFAR classes. So this is a clip model. We just pass the image encoder, the image xi, to the clip, and we get say we get a 512 dimension embedding. And we get the text representations of each of the classes with the prompt, a photo of the class name, and this class name can be the name of the class such as dog, cat, aeroplane, whatever is there in the CFAR10 dataset. Now with this 512 embeddings, we do the correlation of each of these 10 classes representations. So we get a text representation corresponding to each class Z10, and this is Zi. So we pick whichever gives the maximum correlation, and we declare that as the prediction of the model. So this is how we do a zero shot prediction using the clip. So we now go to the notebook and see the implementation of the SimCLR and the clip. So in this tutorial, we will see the implementation of the self-supervised contrastive learning, and a very simple method is discussed called SimCLR. So here we take the augmentations of one image, two augmentations, and two augmentations of the another image, and here we would like to attract the augmentations coming out from the same image and repel from the representations of the other images. So here we just import the libraries. So these are the augmentations being suggested in the clip one. Sorry, the SimCLR one. This is crop, resize, and flip version of the original one, and distort and produce color distortion. And these are some augmentations with rotations, cutout, and Gaussian noise, Gaussian blur, subtle filter. So this is the implementation of the overall picture of SimCLR. Given an image, we form the augmentations of the image, and then we try to maximize the agreement between the images, between the two different augmentations. Of the same augmentations across a different image, we would like to minimize the agreement. As discussed, this is the loss function we intend to minimize. And so this is the SimCLR, and this is an unsupervised way of training. And once we train the SimCLR model, and so here we use the STL10 dataset. And after training this using SimCLR, and we would like to test this on the downstream task of the STL10 dataset. And we only fine tune the classifier here, and just you use a simple logistic regression model. So this is the code for training the logistic regression. And finally, we see the test accuracy when we only have 10 images per label, and we keep increasing the number of labeling data in fine tuning of the downstream task. And we see the accuracy of the test set is increasing. And just to compare this with how the training from scratch of ResNet 18 would behave. When we train the ResNet from the scratch, we just get an accuracy of 73%. So this is 8% less than the contrastive model, and even slightly less than SimCLR achieves with 1/10 of the data. So coming to the clip. Here we load the clip model. So we have ResNet 50, ResNet 101, and VAT base 16, VAT base 32, ResNet 54, ResNet 50, 60 models. So we take the VAT base 16, and this is how we load the clip model. And this is the total size of the model, 151 million parameters. And good resolution is 224, and the context length is 77. Vocab size is 49K. So we do a clip reprocessing of images. We apply the similar transforms as the clip actually applied. And so these are the descriptions. Like a photo of tabby cat, a portrait of astronaut with American flag. For each of the label, we create a prompt, such which is a textual description. And yeah, so once we have this thing and labeled with the images, we now see how the clip actually predicts the two class. So this is the image, and we get the image representations of this image and correlate with each of this um, prompts corresponding to each of this class, and we see the confidence that we get here. And this is a rocket, and this is a candle, and this is a boy, man, and this is a motorcycle. It's pretty high confidence. So this is how the flip zero shot classification is being done. So we will now go over the questions. So the first question is, in the context of self-supervised learning, SSL, the contrastive learning has been widely used for representation learning. So each of the following statements are not true about contrastive learning and its relationship to supervision. Contrastive learning aims to maximize the agreement between differently augmented views of the same data sample or minimize agreement between the views of different samples. Well, this is true. And in contrastive learning, negative pairs are typically formed using artificially generated noise samples rather than real data points to improve robustness or bias. This seems incorrect. And one challenge in contrastive learning is the requirement of large batch sizes or memory banks to ensure a sufficient number of negative samples, without which the learned representation may collapse. And the contrastive learning requires labeled data to generate positive and negative pairs, which is not correct. So A is true, which is because the contrastive learning forces maximizing the agreement between the augmentations of same image and minimize the agreement between the different images. And option B is false. In contrastive learning, negative pairs are typically the real data points from the data set. not generated by noise. And C is true as constructors often require large batch cells or memory banks to gather enough node samples to avoid the representation collapse. And option D is false because we don't need two labels to generate the augmentations. Second question. Several pretext tasks in self-supervised learning use specific augmentations like jigsaw puzzles, rotation, prediction, colorization. These tasks help the model learn useful representation without labeled data, which are the one statements about this pretext tasks and augmentation is not true, as false. So the jigsaw puzzle task involves dividing image into multiple patches and shuffling them, and the model is trying to predict the correct arrangement of patches, encouraging spatial reasoning in visual representations. Prediction as an image augmentation teaches a model to recognize object orientation by rotating the image randomly and training the model to predict which leads to learning orientation in hidden features. Pretext tasks like jigsaw and rotations are designed to improve performance on image classification but are generally ineffective when transferred to tasks like object detection and semantics, which is not true. I mean, in general, any self-supervised training works well on the downstream tasks. The jigsaw task is considered to be invariant to local structure distortion, making it effective in preserving fine-grained details of image given the patches. And this is not true because jigsaw task is aimed to focus on the learning the global representation, not the local structures. So C and D are the false, and this makes them the correct answer. And A is true because it divides the image into patches and encourages the model to learn spatial relationships and has been shown to improve the representation of option. B is true because um, it teaches the model to learn the rotation invariant features. In the SimCLR model, the choice of data augmentations is critical for learning robust representation, which are the following statement about SimCLR's augmentation strategy and its role in contrast to learning are true. SimCLR primarily uses augmentation such as random blocking, horizontal flipping, color distortion to create diverse views, which help in learning invariant features. The use of stronger augmentation such as heavy blurring or noise injection in SimCLR is beneficial for all downstream tasks as it increases the variety of training samples, ensuring the robust presentation. The combination of augmentations in SimCLR is designed to ensure that views maintain enough semantic content to be considered positive place while still being sufficiently different to avoid trivial solutions. Since I use augmentation like random program color tutoring to artificially inflate the size of the data set, making it possible to train with fewer samples while maintaining similar performance of the larger data sets. So A and C are true, and B is false because although strong augmentation increase variety, excessive strong augmentations can harm the model's ability to learn meaningful representations. And C is true because SimCLR ensures that augmented views maintain enough similarity to be considered positive pairs while being different enough to avoid trivial error. D is false because the goal of augmentation is not to inflate the data set but to learn better representation. So in SimCLR model, a batch contains 512 images and each batch generates two augmented views, assuming each augmented view has exactly one positive pair. Calculate the total number of positive pairs and negative pairs in the batch. So since each image generates two views and the total views are 1024 because we have 512 images and positive pairs are 512 and for each positive pair and the total positive pairs are 1024 and for each positive pair um, um, we have 2n minus 2 negative pairs because two correlated views of the same positive pair are, are not negative. So for each data point we have 1022 negative pairs and in total we have 1024 negative points. So these many negative pairs we end up having. So Clip has demonstrated a strong zero-shot performance on variety of tasks by learning geometry representations of images and text. Which of the following statements about Clip's architecture, training strategy, and generalization abilities are true? Clip's contrastive learning objective uses a dot product of image and text embeddings to compute similarities, uh, which are the normalized by softmax function to align positive image text pairs. Clip uses two separate input, one for image and text, where do not project one to single text pair, and the server is used to match the corresponding pairs in the text pair. One of the main reasons Clip performs well on zero-shot tasks is due to its training on wide variety of image text, which is true. And Clip zero-shot are primarily limited to object classification tasks and its fine-tuning on complex tasks such as image captioning and visual question answering require additional fine-tuning. So while Clip option A is false as Clip uses cosine similarities between image and not the dot product, and option B is true, and option C is true. And only Clip, one of the Clip's key strength is its returning a large diverse image text space and learn highly generalizable representations performing well in zero-shot scenarios. Option D is false. While Clip excels in zero-shot classification, its architecture and environment representations are not limited to object classification. Clip has shown promising results in image tasks like image captioning, visual question answering, and other complex tasks without fine tuning. So its performance can improve further with additional training on specific tasks.